So in this question, we have these different compounds, and we want to know which one of these compounds could have a zero dipole moment. And a zero dipole moment, what that is, it is whenever all the dipoles cancel out. So it's when all dipoles cancel out. And what makes a dipole is basically whenever you have two different atoms that are in a covalent bond. I'll put in a covalent bond. And the reason why it's going to be two different atoms is because each atom on the periodic table has a different electronegativity. And what electronegativity is, it describes the pull of electrons within a covalent bond. And so let's, for example, say that I have atom X and it's going to be covalently bonded to atom Y like this. Now, let's say that atom Y right here has a greater electronegativity. If this Y right here has a greater electronegativity, it means that the electrons in this bond right here are going to be closer to the Y than to the X. And because electrons are negative, it means that this Y right here is going to be a delta negative like this. And this X right here would be delta positive. And so this is what a dipole is. And the way we would show this would be to put a small line here and then put a large line like this and then put an arrow right here. And this is a dipole. And for a zero dipole moment, we want to get all the dipoles like this to cancel out. And so in this example, I have the X right here and the Y right here, and the arrow is pointed to the right. Well, this dipole, in order for it to cancel out, I would need an arrow to the left that's the same magnitude, but opposite in direction. This one's going to the right. I need the same magnitude of it going to the left. And so what we want to do is we want to look at these different compounds, and we want to take into account the pull of the electrons in each of the bonds, and we want to take into account the shape of them, because if one is pulling to the right and one is pulling up, for example, then those could not cancel out, because going up, you need one to go down, and if you're going to go right, you need one to go left. And so we're given the shapes here, but in order to get a better idea of what these shapes look like, we need to pull up a table called a VSEPR table, and that stands for valence shell electron pair repulsion. And so let's pull up that table. So here is the VSEPR table, and the shapes that we have to know to do this question are going to be the tetrahedral, the square planar, and the seesaw. And so those shapes are going to be right here. Here is the tetrahedral, and then here is the seesaw, and then here is the square planar. And so now that we know where all of these shapes are, what we can do is we can draw these different compounds out, and we can look at the bonds and the geometries and figure out which one would have a zero dipole moment, or which one would have all of these bonds, these dipoles cancel out. And so let's take the Cu right here, and we're going to put that in the middle right here. And so what I'm going to do is I'm going to put the Cu down here, and this bond going up here can be bonded to this Cl here. So I'm going to put a bond here and then put a Cl there. And then we have this bond here that's going to go in the plane along with this bond here, and this could be the other Cl. So we're going to put a bond here and that Cl there. So we have the two Cls there. Now we have the two Fs in here. And so this bond in here is going to be going towards us. So I'm going to put a wedge like this, and I'm going to put the F right there. And then this bond right here is going to go away from us. So I'm going to put a dash like this, and then put the F like that. Now, I didn't do the lone pairs in this structure right here, and that's because those lone pairs are not going to be important in order to do this question. And so what I want to do is I want to think about this in terms of how these vectors are arranged. And so if I have this bond here going straight up like this, then I'm going to need one that's going to go straight down, in order to cancel this out. And that's not going to be this one right here. This bond right here is coming towards us. And so what we have here is this right here is going to be pulling with one strength, and then this right here will be pulling with the same strength. But these are not in opposite directions. They're both kind of going towards like this direction over here. And then I have this one right here and this one right here. Now, if these were the same, like if I had CL here and CL here, these could cancel out like this, and they could all have a zero dipole moment. But because these right here, the CU and the F right here, are different from CU and then CL, it means that this dipole there cannot cancel out with this dipole there. And so this molecule would actually be polar, and we want this to be nonpolar because nonpolar molecules have a zero dipole moment. And so we could also say zero dipole moment, or we could just figure out which one of these is going to be non-polar. And so this one right here, we just said this one would be polar. So this is not going to be the answer that we want. Now let's move on to B right here. And in B, it says square planar. Well, a square planar, that's going to be this one right here. And this one, this shape, this is basically like an X. If we look at it from the top going down, it's going to be like an X like this. And so we can put this PT right here in the middle. So I'm going to put the PT here. And then what I'm going to do is I'm going to put this bond here. It's going to be right here. And so we can put a CL here. So I'm going to put CL. And then this bond in here could be the F right here. So I'm going to put the F there. And then maybe this bond right here is going to be the other CL. And then this bond in here could be the other F like this. Now, if we think about this in terms of these dipole moments or how these are orientated, you want to keep in mind the three-dimensional shapes of this. It kind of looks like this one, but it's not. This one is, if you're looking top down, it is makes like an X like this, and this one right here is coming towards us, and there's none that's coming towards us in this orientation if we're looking at it from top down like this. And so you can see how this vector here, if we this bond right here, would point up and maybe to the right like this, and then this one right here would point to the left and up like this. Now, in order to get the exact direction for this, you would have to know the electronegativities difference between this one and this one, and the one that's going to be more electronegative, that's the way the arrow is going to point towards. But it's not really important for this question, because for this question we just need to know are they going to be different or the same. And so what I mean by that is, like this one right here could be pointing up and to the right. Well, we need one that's going to go down and to the left like this, and this one right here would have to be the same as this one. So because this one here and this one here are both going to be different, it means that this dipole cannot cancel out with this dipole because they're different like this. So this one's going to point this way and this way, so this one could point maybe like this, and then this one, and then this one, those can point maybe like this. Now, if it's in this orientation, this would be a polar molecule. But if we take these atoms like this, and let's say instead of putting the Cl here and the F right here, let's say we did this. Let's say we put the F here and the Cl here. Well, now when we go to look at these vectors, this one's going to be pulling this way, and this one will be pulling this way. So now if you look at it, this vector there and then this vector there, or this dipole there and this dipole there, those will now cancel out. And so this vector there and this vector there, or those different dipoles, those would also cancel out. And so this one right here would be non-polar. So this could be non-polar if it's in this orientation. And notice the question says, which one of these could have a zero dipole moment? Well, this one could have a zero dipole moment if it's faced this way like this. And so now that we know the answer is obviously going to be B, let's see why the answer is not C like this. And so if we look at C, it's going to have a seesaw, and a seesaw looks like this. And so if we can imagine this S right here is going to be right here, we can put the S down kind of like this. And then let's say that the one going straight up, we can make that the CL. So I'm going to have the one CL there, and then the one going straight down, let's say I make that the CL there. And so you can see here, that this one is S to Cl, so it's going to have this dipole, and this is S to Cl, so it's this dipole. These two dipoles are going to be the same because those bonds are the same. They're both an S bond to a Cl. But the reason why this cannot be a nonpolar molecule is because I also have bonds here and bonds here for this seesaw like this. And what is going to go there is going to be the F there and the F there. So these two bonds here and here, they are the same, but if you look at the geometry of these, this one is pointed kind of like maybe like well, the way I have it drawn, it's up and to the left, and this one's down and to the right. And so in order for us to cancel this one out, we would need one that's going to go down and to the right, or at least how I drew it like this. And so this one would also be a polar molecule. This one will be polar. And then the tetrahedral, that's going to be the same as A, like we already explained, so it can't be D either. And so the answer choice that you want to pick is going to be B.